In this lesson, we're going to learn about hybrid orbitals that allow us to explain equivalent energy bonding in molecules. I'm going to start off with the molecule BF3, boron trifluoride, and take a look at this idea of equivalent energy bonding. That is, all three fluorines around that central atom must take the same amount of energy to break any one of those three boron fluoride bonds. If we take an isolated boron atom, it has a valence of 3. It has 2 electrons in the outermost sphere, that is the 2s, and it has 1 electron in one of the dumbbells, in one of the 2p orbitals. So it starts off with 3 electrons, and these 3 electrons, these 3 valence electrons, are not going to have the same energy. So we're going to see that 2 of them are in that sphere, and 1 of them is in that dumbbell. Now what we want to do is we'd like for all 3 of these electrons to have the same energy to account for this idea of equivalent energy bonding. So when the surrounding atoms come in, they can all have the same equivalent energy. So right now they do not. So if you look at an isolated boron atom, as you can see, the 3 valence electrons do not have the same valence energy. So what we want to do is we want to hybridize them. We want to blend them. We want to mix them together so that they all have the same energy. Upon mixing these atomic orbitals together, you create blended orbitals or mixed orbitals, or if you will, sometimes called hybrid orbitals. So let's go ahead and hybridize. Let's mix our orbitals. Upon mixing, notice that they all have the exact same energy now. We're going to call them hybridized orbitals. What I want you to notice is the number of hybrid orbitals created is equal to the number of atomic orbitals that you're able to put in. So we put in 3 atomic orbitals and we're able to get out 3 hybrid orbitals. Now they are all blended, they are all mixed, all the electrons have the same energy, and these hybrid orbitals no longer have the spherical shape of the 2s. They no longer have the dumbbell shape of the 2p. It's actually blended now, so they have equivalent energy with the same shape. Now we did not have to use one of the dumbbells, so it's going to stay unhybridized. What are we going to call the hybrid orbitals? You name them based on the atomic orbitals that went into making them. So you had to put in 1 sphere and 2 of the dumbbells. So the names will be sp2 hybrids. So let's actually take a look at this. What we are seeing right now is an isolated boron atom before any hybridization has taken place. So we have the 2 electrons in the outermost sphere, and you see the 3 dumbbells, and we see an electron in one of those dumbbells. So this is prior to those surrounding atoms, those fluorines coming in trying to bond. Now once these fluorine atoms, these surrounding atoms start coming in, these outermost valence orbitals are going to hybridize, and when they hybridize you're going to have 1 electron in each, all with the same equivalent energy, ready for the fluorines to come in and bond. So we're going to have our fluorines start to approach, and as these fluorines come in, that central atom is now going to get ready to hybridize. So let's hybridize those outermost orbitals. We're going to blend those orbitals, we're going to mix them. Proper word here is hybridize. And notice that 3 of the atomic orbitals now just became 3 hybrid orbitals. They're all sp2 hybrids, they all have an electron in them, they all have the same energy. So now we're ready for the fluorines to come in and overlap and create a sigma bond, a single bond, that is a sharing of 2 electrons directly between the nuclei of 2 adjacent atoms. So let's go ahead and bring in the fluorines and let's create those 3 sigma bonds. And now you see the bonding that occurs in BF3. So what we have here are 3 hybrid orbitals to explain the equivalent energy bonding in BF3. Hybrid orbitals that allow us to explain equivalent energy bonding in molecules. I'm going to start off with the molecule BF3, boron trifluoride, and take a look at this idea of equivalent energy bonding. That is, all three fluorines around that central atom must take the same amount of energy to break any one of those three boron fluoride bonds.